Good afternoon, A.U. Patel sir. Good afternoon, Brijesh sir. I, Dr. Jaimini, welcome you on behalf of KCG in this webinar series on emerging technologies. This is our third session on the topic machine learning for natural language processing. This webinar series is a great initiative by our CEO KCG, M. Nagarajan sir, so we are thankful to him also. Firstly, I would like to request Professor A.U. Patel sir, an advisor KCG and a former Vice Chancellor of Gujarat University, to give a warm welcome to Dr. Brijesh Bhatt sir.
Good afternoon to everybody. We welcome our honorable Director and CEO KCG M. Nagarajan Sahib, Dr. Brijesh Bhatt, Professor of Computer Engineering Department of Dharmsinh Desai University, Nadiad, Dr. Brijesh Bhatt is a well-known person and he is also expert in machine learning and other emerging technologies. His achievements are very large. One of the only two Indian programs committee members of the first World Conference on Technology Education and Multilingualism, invited as a researcher at most prestigious research institute of Russia, Russian Academy of Science, Moscow, Distinguished Facilitator Award 2016 by Infosys, Program Committee member of calling 2012 IIT Bombay the top conference in the field of natural language processing, reviewer for Transaction of Asian Language Processing Journal, reviewer of International Conference on Natural Language Processing. We are lucky that he agreed to deliver this lecture on our webinar of emerging technologies. We are going to hold nearly 50 such webinars continuously every week, and also at the same time some other fields of social sciences, languages, etc. If we look at the history of machine learning, it was in the 1940s when the first manually operated computer system, electronic numerical integrator and computer, was invented. Machine learning became very famous in the 1990s. The intersection of computer science and statistics gave birth to probabilistic approaches in artificial intelligence. This shifted the field further towards data-driven approaches. Artificial intelligence, machine learning, deep learning journey from 1950s, 1980s and 2010. If we see the advantages, Brijesh, but will explain everything, but just I am giving you general idea that application of machine learning is very large, and this will be a very highly useful technology in future, in which image recognition, automatic language translation, medical diagnosis, stock market trading, online fraud detection, virtual personal assistant, email spam and malware filtering, self-driving cars, product recommendations, traffic predictions, speech recognition. So application is very large, and data acquisition, time and resources, interpretation of results, high error susceptibility. These are most prestigious advantages. And this machine learning and other emerging technology will shape our future life and will change drastically our daily life and also our total social life. I am highly again thankful to Nagarajan Sahib and also to Brijesh Bhatt, who is going to deliver extraordinary lecture on this webinar series. Again, I welcome you all. Thank you very much.
Thank you so much, A.U. Patel sir. This was such a warm welcome to Brijesh sir. A.U. Patel sir, I would like to ask you that is Nagarajan sir going to join us or we shall start with the session, sir?
No, he is very, very busy with other matter. So
Okay.
please start.
Okay. Further, I would like to request the speaker, Dr. Brijesh Bhatt sir, to proceed with the session.
Thank you, A. Patel sir, for your kind words, and thanks for inviting me for this talk. I hope you all will enjoy the next 1.5 hour of our discussion, and also we will have fruitful discussion and question answering. So thank you, KCG, for this invitation, and with that we'll begin with our presentation. Let me share the screen. Good afternoon to all participants. This talk is on machine learning and its application for natural language processing. We call it briefly as ML/NLP. I am Brijesh Bhatt. I am working at Computer Engineering Department of Dharmsinh Desai University. And yeah, with that, let's begin the session, and I hope you will enjoy the discussion. The basic outline is we'll talk about machine learning, then we'll talk briefly about natural language processing, and then we'll talk about various natural language processing problems which can be solved using machine learning techniques. So let's begin with what machine learning is. So machine learning explores the study and construction of algorithms that can learn from and make prediction on data. So basic core idea at the core is learning from the data. And as we can see, the definition was coined in 1959 by Arthur Samuel. So it is not that new field, but recently it has grown in prominence, and we'll see why it has become prominent these days. So machine learning is employed in a range of computing tasks where designing and programming explicit algorithms with good performance is difficult or infeasible. So there are many tasks where traditional programming paradigm doesn't work. We'll spend some time on discussing about those tasks also and about the traditional programming paradigm also. But some example of such tasks are applications like email filtering, detection of network intruders. Email filtering means all the mailbox nowadays, Gmail or any other mail services which you might be using. The mails automatically goes to spam. The machines are capable enough to detect whether the mail is spam or not. That is email filtering. The detection of network intruders. The network, various attacks on the network are also detected very intelligently. Then speech recognition, a very old problem and still a relevant problem, where we want to identify the person who is speaking and also the text that is being spoken. So converting speech data to text and text data to speech are also a very challenging and relevant research problem. Then recognizing people, face recognition. We all have biometric systems installed on our offices these days, and this system needs to be more and more intelligent. So there is face recognition. Then playing games like chess, checkers, machines can also play this kind of game. We had news few years back that the chess has become the the computer has become the grandmaster of chess. So machines are becoming more and more intelligent. But the first question that we'll try to ask is, can we solve the above problem using traditional programming? Answer may be yes or no. In both cases, we will try to see why we can or why we cannot. So let's spend some time on traditional computing versus machine learning. So most of the problems that we solve using machine learning methods are usually optimization problems, where we try to maximize or minimize some objective function. Computation time required through traditional methods is usually non-polynomial for the kind of problems that we are discussing. And we know from our algorithm theory that the problems which cannot be solved in polynomial time fits in the category of NP complete or NP hard problems. So the traditional paradigm says that these problems cannot be solved in polynomial time. You need to do something better than that. So if we can solve using traditional program, then machine learning is not required. But there are some known problems which cannot be solved in polynomial time. So technically, actually, all the machine learning problems that we are formulating and discussing can be proven to be in this NPC or NP hard category. For example, this learning of Bayesian network is a NP hard problem. So you can deduce from this that other machine learning problem can also be NP hard. Besides the kind of problems we are dealing with are learning problems. So not just that they are hard or the optimization requires exponential time, but also these are different kind of problems which require certain amount of learning. And that leads us to the next question, that is, what is learning and what is learning problem? So let's define something called well-posed learning problem. So a computational program is said to learn from experience P with respect to some class of tasks P and performance measure P. If its performance at task in T as measured by P improves with experience E. So, for example, before we elaborate on this, let's talk about an example that handwriting character recognition learning problem. Right, recognizing someone's handwritten characters. So, handwriting recognition learning problem, has task called recognize handwritten word image. So, we take word as an image and we process that image and recognize whose handwriting is this. Performance is percentage of words correctly identified. How many words are correctly recognized? And experience is a database of handwritten words with given class label. So if you want to develop a handwriting recognition system, you need a database which contains a set of handwritten characters or words of the language. For example, alphabet A to Z, handwritten and correspondingly correct mark of the alphabet. So alphabet A is typed in only one way, but it can be written in many different ways by different human beings. So all this different representation of the typed alphabet A will be mapped to the correct typed alphabet A. So that is our database for learning. And then you expose the system. You expose this database to the system or the subject, and subject would look at all these words and start understanding what the word or what the character represents, or what is the correct type character or the word for the given character or word. So learning is something which improves with period of time. So that is also why I say that these are different kind of problems. So we are given a task and we are subjected to some experience of that task. And with our experience, our performance at that task would improve. If it improves, then we say we are learning. Otherwise, we are not learning. So the machine learning is essentially about this kind of problems where you keep on improving as you gain more and more experience. Human beings do this all the time, right? Like define driving vehicle as a learning problem. We all have learned to ride bicycle, and no one has, and we all have fallen down while our first or second attempt of riding the bicycle. Similarly, playing chess is a learning problem. You keep on improving. You can never master this, but every day you can be better than what you were yesterday. So you keep on learning on this. So in that sense, chess playing is also a a learning problem. So the key aspect of learning problem is uh, you are given a task and with experience you can keep on improving on that task. So you need T, P, and E, three parameters to define a learning problem. P is the task given, P is the performance index, and E is the experience. So if you see this kind of thing, then you can think about machine learning. Then you see that it is a probable machine learning problem. So now let's come to the focus of today's talk, that is learning a language. So we say that we want to explore the natural language processing problems which can be solved through machine learning. So let's talk about some language related problems which are classical machine learning problems. So learning a language includes listening, understanding and speaking, reading, writing and understanding text, and translating text from one language to another. All these are considered as very difficult problems. In fact, the very early test of machine's intelligence, known as Turing test, even today people do that competition, and every year winner of the test is announced. So that test is about you are in a room, you are a moderator, you are in a room. On one side there is a person sitting, on another side there is a machine, and there is a partition between person, machine, and you. So you don't know at which side the person or machine is sitting. Now, while the person and machine are interacting, you can see and observe that conversation. So, while observing the conversation, as a moderator, your task is to identify on which side the person is sitting and on which side the machine is sitting. If you can not identify this, then the conversation agent, the program through which the person and machine are interacting, has passed the Turing test. So, actual test of intelligence is how well machine learns language. And this is really a difficult problem for machine, which is being investigated for many decades. But just imagine how easy or how soon, as a human being, we learn this problem, or how soon we start mastering this problem. For example, the second bullet, the first bullet, listening, understanding, and speaking. This first bullet is something that we learn when we turn of the age of what, 1 or 2 years. Every 2 year or 3 year old kid at the most would be able to listen and speak words, though the person cannot read or write. It takes schooling to learn to read and write, but before that person starts uh, to listen and speak. Compare this with machine and see how difficult it is. We are still struggling with developing a very robust speech recognition or text to speech or speech to text conversion system. On the contrary, a 1 year old, 2 year old kid can easily start speaking of words, can start recognizing voice of mother and father, even when the age is around 5, 6 months. The kid would identify the voice of mother or father, will start uh, understanding what mother or father is saying around 1 year, and around 2 years they start speaking it. So the most complicated and most intelligent problem we started solving at very young age of 1 or 2. But have we mastered this? Have we mastered the language? Have we solved the problem? I'm asking this question to ground the definition of machine learning that we had discussed, which talks about performance. Performance, right? We are given a task and we are given a performance. And with experience, we keep on improving. So we cannot say that we have mastered a language or we don't make any mistakes while speaking or while writing a language. We still make mistakes, but we are improving with days. We are improving with our experience. So this is one of the key idea of machine learning problems. And these are the key problems like listening, understanding, speaking, which maps to speech to text, text to speech, voice recognition kind of problems. Reading, writing, and understanding text, the text data, has become much more interesting problem these days. Simply for the reason that in last couple of decades, the data available online, data in text form available online has grown immensely. So there is a lot of blogs, there are a lot of social media, social networks where people keep on posting messages. So earlier days of internet, we used to see what is given on the website, but nowadays we use website to post our ideas, right? So we all keep on writing. So we are all fond of messaging, we are all fond of writing, and this has led to tremendous growth of data in text form. And so many companies are after this. So many companies wants to do a lot of business around this, wants to build a lot of intelligent system around this so that the user experience would keep on improving. So that's why the text processing has become a lot more interesting in the last couple of days. It's not that it was not interesting earlier, but at the turn of 21st century, I guess it's become much more interesting and challenging. And then a very standard and age-old problem of translating text from one language to another. We all want to read the material available in different languages. Because if you don't know the language, you don't know the culture, and you cannot gather anything about that culture or those people. So that's why machine translation has always been a fascinating problem. There are cultural needs, there are political needs, and there are security needs also. Cultural needs in the sense that if you want to learn Marathi or Bengali culture, then you need to read those authors, and for that you need to learn that language. Political need because, a, like, for example, in India, a multilingual country like India, the state ruling is done in regional language, and central ruling is done in the national language, which is Hindi or English. So when a issue is passed from the state to center, a lot of time is spent on translating the material. This happens in the court cases also, local court to high court to Supreme Court. When the case travels, it changes the language. Local courts might be operating in local languages, but the Supreme Court would read English only. And when you translate those case documents from one language to another, you lose the sense of the case. And then the judgment can be different. So there are political needs, there are cultural needs, and there are security needs also. We need to know, we know that the terrorists or other organizations which are threat to security communicate with certain code words and encrypted languages. We need to decode that, and for that also we need translation. So translation has remained a challenging problem. So there are so many things that we can do with the natural language process, and where machine learning can help. Some examples of what we are discussing. For example, the welcome to class, the first sentence. So what is this blank represent here? The blank represents the system is capable to identify what will be the word between to and class. Right? Usually it should be a determiner to the class or to a class or to word completing. So nowadays the systems are capable to do this kind of thing. On the right side, look at the task. That task one is single supporting text. Mary went to the bathroom. John moved to the hallway. Mary traveled to the office. Where is Mary? So if you give a sequence of sentences to the machine should be able to get the correct answer. In this case, the answer is office. It went to office. So after bathroom, the next sentence was office. So it picked up the office. So machine should be intelligent. And of course, we notice that these are not difficult problems for humans. We do all this time. Then machine translation, as we said, has always been a challenging problem. And also speech recognition. This too has always been a problem of challenging and interesting problem. On the bottom left, the problem right side shows the book stack and left side shows the book stack and right side shows summary. So read so many books and generate a summary out of that. So that is called a problem of text summarization. Nowadays, a lot of information is available on internet through different media, and usually we do not have time to walk through all this, read all this, and get gist of it. So what we want is we want some short announcement, short message which will give us the idea of what is going on. Hence, Twitter and WhatsApp forward and all that. It conveys the things in very few words. So text summarization systems would help users and save a lot of online time spent to understand few things. And the bottom right is a conversation agent. Call it chatbot or call it question answering system or call it personal assistant. So one side is machine, another side is human. As I said, this is a standard structure of Turing test, which keeps on improving over the years. So what we had in terms of personal assistance in 1960s and what we have now in 2020 in form of Google Home Mini or Alexa or Cortana. They're much more smarter, right? And they pick up much more information from us than we could have imagined in last couple of decades. In that sense, uh, it is an interesting problem and it keeps on improving over the time. And it is not that the ball has not been rolling. The things have already become start. The people have already started solving this problem to an extent. And we are in our day-to-day use of internet. We have observed this. I'm not sure whether we could actually relate to any famous NLP problem with this or not, but we do it all the time. For example, in top part, I have just fired a query to Google search engine and asked the question, why did Kadappa kill Bahubali? And look at the answer that Google has produced. Bahubali stood against his kingdom to marry Devsena, so he left Mahasmati and seeing this as a threat, a newly appointed king Ballaldev wanted him dead. Katappa killed Bahubali because it was his duty to secure the king of Mahishmati and he is a slave of the throne, as he said in Bahubali 1. See how precise and accurate the answer is. If you search uh, internet about Bahubali, there might be hundreds of web pages that you might come across. But out of all those pages, Google has picked up this as the best answer and it has represented this. So the things that we are talking about, understanding the meaning, understanding the written language, summarizing the information from the plethora of text. So all these things are already being done and up to this level of accuracy. But still there is a lot of scope. We'll see that with example. On the bottom side of the slide, if you see, I just write a sample mail and I was typing HELL. So when I typed HELL, if you see, the assistant would give me the possible words that I might want to type, like HE-LL, or you want to say hello, or you want to say hello in Gujarati, or you want to type help. Right? So transliteration, converting text from one language to another, that is transliteration task. HELLO in Gujarati, hello. And auto completion, that is predicting the next character to auto complete the word. Both the things are going on in this simple on the fly word completion system or suggestion system. And see how intelligent it is. But you know, it is just frequency based. The words which you type frequently will come up there. So such a simple technique can also lead to such a high quality solution. Next in the application is I tried to search Taj Mahal. When I search Taj Mahal, Google not just locates the Taj Mahal as a something it is located in Agra, but it also tells me the direction, it also tells me the website, it also tells me location, and it also gives me images. All these things, of course, fetch from Wikipedia and Google Maps, but it knows, right? So there is only Taj Mahal. So this is named entity disambiguation. It can figure out which named entity we are talking about, which location we are talking about, which place we are talking about. We will see that this is also an interesting problem, but see, this is the accuracy we are witnessing these days. Then a few days back, I got this message from a undergraduate student on LinkedIn. A student was asking for some help, but this is what LinkedIn suggests me. What should I type? Should I say hi Shivam, or should I say thumbs up, or should I say sure? Right? So this is also we are witnessing in all the chat applications. Like it will construct reply for you. So this kind of conversation agents or chatbots that we are referring to, it can give you the suggestion that what can be answered to the particular message. So machine have become intelligent to predict that what can be response for the given message. And below that, if you see the two examples of English to Gujarati translation. And English language is also auto detected, as you see it is saying English detected. If I type I miss you, it gets translated in Gujarati as હું તમને યાદ કરું છું. And if I type I missed the train, it gives the answer હું ટ્રેન ચૂકી ગયો. Both the translations are near perfect, I guess. But if you have noticed, it could disambiguate the word miss. Miss has more than one meaning. Here we are talking about two meanings of miss. One is miss in the sense of remembering. Actually, miss and yaad karu are not exact synonyms, if you notice. Uh, yaad karu is remembering, right? But in the meaning of miss, in sentence I miss you, is not present in Gujarati. We don't have any word to translate this miss exactly. And usually we say that હું તમને યાદ કરું છું. So there is fluency wise, the translation is perfect. And we do not have exact word of miss. That also is known to the machine now. And when I say I missed the train, miss means ચૂકી ગયો. So we have a word, હું train ચૂકી ગયો. Yeah, so this is machine translation in action. And all these things are taken from all these last 2-3 slides where I have cited the examples are taken from the website. So it means that the systems are in place and people are doing this. But also notice that most of these things are for English language. Not much has been done for Gujarati. We'll talk about that also if we get some time. Yeah, so with that, let's come to natural language processing. What is it? And so all these problems are solved using natural language processing. All these problems are actually natural language processing problems solved using machine learning techniques. So let us see what is natural language processing. So natural language processing is the task of process information contained in natural language, also known as computational linguistics, human language technology, or natural language engineering. And a broader question that we ask here is, can machine understand human language? Of course, define understand because it also keeps on improving as we have seen the learning problem. So understanding is the ultimate goal. However, one does not need to fully understand to be useful. As we said, we start speaking at the age of 2 or 3. Of course, we don't understand the language completely at that age. Even today also, we cannot say we understand the language completely, but we keep on improving. So reach to a level where we become useful and then we keep on improving. So the natural language processing involves analyze, understand and generate human languages just like humans do. It is about applying computational techniques to language domain, to explain linguistic theories, to use the theories to build systems that can be of social use. It started off as a branch of artificial intelligence, but it borrows heavily from linguistics, psycholinguistics, cognitive science, and statistics. It makes computer learn our language rather than we learn theirs. So these are the stages of NLP: phonetics and phonology, morphology, lexical analysis, syntactical analysis, semantic analysis, pragmatics, and discourse. Yeah, so we are talking about stages of NLP: phonetics and phonology, morphology, lexical analysis, syntactic analysis, semantic analysis, pragmatics, and discourse. We'll look at this stages one by one. We'll define that. We'll identify challenges of this, and then we'll see how it can be solved using machine learning methods. So phonetics is a task of processing speech. Challenges are homophones like bank versus bank. So bank is a financial institute and bank is a river bank. Then example of Hindi, near homophone, matra versus matra. So when we are speaking, usually we don't emphasize enough to get the clear context, to convey the words clearly. But through context, people can pick up. So matra versus matra, they are called near homophones. Then also word boundary is a challenge, like आज आएंगे या आ जाएंगे. So आ जाएंगे as will come or आज आएंगे as will come today. So while you are processing speech, you need to define the word boundary. You need to know where a word breaks and next word starts. So that is also a problem. Like I got you a plate. Usually we mix up the words. Got you a plate. I got you a plate, but we call it I got you a plate. Then phrase boundary, where a phrase stops. We don't pause on comma or semicolon every time or full stop. And that's why usually when we read a long sentence, machine might miss the phrase. Like MTech 1 students are especially exhorted to attend as such seminars are integral to one's post-graduation education. And then there are a lot of disfluencies like and you might have noticed me also doing this all the time. So this should be removed while you are processing speech data, and proper words should be extracted. So that is first stage. If we start a natural language processing task from the spoken language, then first step is to convert the spoken form into written form, construct the text, construct it into text. And then all other steps involve text processing. And first of them is morphology analysis. So morphology is finding the root word from the given word. So it is about word formation rules from root word. For example, noun, plural, and noun has plural or gender marking. For example, boy and boys. So plural boys needs to be mapped to the root boy. And why we need to do this? For two reasons. One is that dictionary contains entry only for the root word. So if you want to get meaning of a word, you need to look into dictionary. And to look into dictionary, you need to go to the root form. And second thing is the inflection or the words or the letters before and after the root word actually conveys something. For example, when I write boys instead of boy, I want to convey that there are more than one boy. So this S is a plural marker that we need to know. So that's why to get the meaning of a word and to get additional information through this extra inflection, these two things are done at morphology level. For example, gender marking is like Zar and Zarina. So we know that Zarina is a feminine, Zar is a masculine. Similarly, for word, we have tense marking like stretch and stretch. So when we put ed at the end, we know that we are talking about past tense. So that marking is also important. So when I talk to my friend and I say that I played cricket today, so it means that I am not playing now. I have used the past tense marker ed. So machine needs to know that. So the sense of place, sense of number, sense of time, all these things are covered through this inflection. So tense, then aspect like perspective, seat, headset, modality like request, khana, khaiye. So all these are hidden inside the inflection of a word, which is extracted through morphology analysis. So this is the first crucial step in NLP. There are many languages which are rich in morphology, like Dravidian, Hungarian, Turkish. There are many languages which are poor in morphology, like Chinese and English. But actually, it it depends. Like if the morphology is poor, then the morphology processing might be easier, but later stage processing might be difficult. On the contrary, if the morphology is rich, then morph processor might be difficult, but the later stage processing might be uh, difficult. One traditional way or interesting way of solving morphology analysis is through finite state machine. We will see that in our example. So once we have identified the inflections and extracted words, uh, we are done with the morphology stage. The next stage is lexical analysis stage. As I said, from the word, try to get the dictionary meaning. Find out the dictionary meaning of that word. That is the next step. For example, if you search for a word dog, dog has many properties attached with it, lexical and semantic, both. For example, it is a noun, which is a lexical property. It takes S in plural, which is a morph property. It is an animate. This is a semantic property. We are talking about semantics of being a dog. So there is animate. It has four legs. It is carnivore. These are semantic properties. And challenges here is a sense disambiguation at lexical level and also at semantic level. Because when we say I use word dog as a noun, it can mean two things, right? Dog as the animal dog, or sometimes we also call some detestable people dog. So that detestable person can also be referred as dog. So we need to know which dog we want to use in the sentence. So this is part of lexical analysis. So we are at stage where the speech data is converted into a sentences. The sentences are broken down into words. The words inflections are removed and meaning of the word is mapped from the dictionary. We got the lexical property of the word. And then we are at the next stage of processing where we process the structure of the sentence. Usually sentences follow strict grammar rules to structure words. For example, English follows noun, verb, that is subject, verb, object property. So first is subject, then verb, then object. Like I like mangoes. So I is noun, subject, like is a verb, object, and mangoes is again a noun. Like is a verb and mangoes is a object. So subject, verb, object properties uh, is followed in case of English active voice. And we also need to detect how many noun phrases are there and how many verb phrases are there. So NP and VP detects the noun phrase and verb phrase. A sentence is made up of phrases, and phrases are ordered in terms of subject, verb, and object in English. So understanding this is called syntactic processing of language, syntax processing part. And this part is important because different language follows different syntax process. I am sure while I was talking about English, you could have related with the case of Gujarati, and you would have noticed that Gujarati follows the subject, object, verb property, right? May carry khadi. The verb is the last part of the sentence. In case of English, I like mangoes. So if you are thinking about developing a machine translation system, then you need to know the difference between the structure and rearrange of the words so that the target language structure is preserved. Right, so that is structure detection part or syntactic processing part. There are many challenges or ambiguity appears during this syntactic processing. One is the problem of scope. For example, the old men and women were taken to safe locations. Now, what is the scope of the adjective old? Will it go with men only, or it will go with both men and women? So if you see the second bullet, I have put it in brackets so that it can be clear. Old goes with men and women both versus old goes with men and women. So which looks more appropriate? The answer is not that simple. The answer lies in the way we are cultured. Right? Because who do you want to protect? That is a very cultural thing. We want someone to be taken to safe location. So that someone is only old men and old women or old men and all women. So our culture tells us that it should be old men and all women. So see how complicated the processing of language can be. Another example is no smoking areas will allow hookahs inside. So what does it mean? The no goes with the phrase is smoking area or phrase is no smoking area. If it is smoking area, it means that smoking area will not allow hookahs inside. But if we are talking about no smoking area, then the meaning is different. Then it says that there are some no smoking areas which allows hookahs inside. So there is an ambiguity of scope while you are doing the structure processing of breaking sentence into noun phrase and verb phrases. Then there is a problem of preposition phrase attachment. I saw the boy with a telescope. So who is holding the telescope? You or the boy, or I or the boy. That cannot be figured out from this. So where do you attach the phrase a telescope? It goes with boy or it goes with I. Then if I say I saw the mountain with a telescope, then maybe I can figure out that I am holding the telescope because mountain cannot hold telescope. But the answer is not from the grammar of the language. Answer is from the world knowledge. You know that mountain cannot hold the telescope. That's why you say that I hold the telescope. Then I saw the boy with the ponytail. So now I know that ponytail attaches to the boy and not to I because I cannot be an instrument of seeing. Sorry, ponytail cannot be an instrument of seeing. Similarly, there is a headline in the newspaper like 20 years later, BMC pays father 20 lakhs for causing son's death. And the question is, who has caused son's death? BMC or the father? Of course, father would not kill his son, and even if the father kills the son, BMC would not pay. Right? But that is our pragmatics that we can figure out from the pragmatics. The grammar and the language doesn't say anything about where do you want to attach this causing son's death. So these are the examples to make you realize that how difficult it can be to process the text data. So this was up to the syntactic processing, and beyond that it is more complicated. But this, as we have discussed through example, these are the tasks of semantics, pragmatics, and discourse. We need to know about semantics. Like as I said, I saw the boy with a ponytail. Then ponytail cannot be an instrument of seeing. That is our semantics. We know what does ponytail mean. So that's why we could say that ponytail is not an instrument of seeing. Then this old men and women example, which is an example of pragmatic, where the way we are cultured tells us that we want to make all our women safe, not just the old women, but all women. So that's why old men and all women were taken to safe locations. And this discourse, like no smoking area, allows hookah inside. If you look at the remaining of the phrase, if you add some more phrase, then you would be able to disambiguate it. So no smoking areas allow hookahs inside, except the one in Hotel Grand. So there is an hotel which allows. So after that, the meaning would be clear. So when you need to look at the other sentences to make sense of the sentence or phrase that you are currently processing, it is a task of discourse. You look around to and of previous information and next information, and then you make sense out of the sentence. That is called discourse processing. Yeah, so these are the stages of NLP, and then we will come. Now we will come back to the case study of the various NLP problems that we want to discuss. I have chosen these 5 problems out of all the things that we have discussed: morph analysis, part of speech tagging, text summarization, question answering, and semantic and knowledge network if time permits. Otherwise, we will go to some of the work that we have done. Yes, so we are talking about case study of some famous NLP problems like morph analysis, part of speech tagging, text summarization, question answering, and so on. So let's take them one by one. First one is morph analyzer. Let's try to define let's try to see what morph analysis is. Like computational morphology is defined as the study of computational analysis and synthesis of word from forms in the context of NLP. It is about processing and producing language computationally at word level. And knowledge of words include word structure and word formation rules. For example, if you, as given in the block on the right side, Chokrao Ramshe. So if you do morph analysis of this, you will get output like this curly bracket shown below. That Chokro is a noun and a plural marker. It is a plural form. Then Ramvu is a verb and Ramshe is a future tense. It is a tense marker that it will play. So imagine the scenario where you want to translate this into English. So what do you need to do is you need to understand the word, its meaning, and find out the corresponding English word from the dictionary. Then you need to convert the inflections of Gujarati into inflections of English. And the third step is reordering of the sentence. So finding out word from Gujarati to English is a dictionary lookup. So you look at the dictionary and convert Chokro into boy, Ramvu into play. And you have also stored morphological markers. So convert them also. One is plural, second is future tense and verb. And then construct the English word. So boy with plural marker is boys. So Chokra O gets translated to boys. Then Ramshe will get translated to will play. So you are introducing a new word in English, will. So Ramvu is play, but you also figure out that since it is a future tense, you need an auxiliary verb will, and it makes boys will play. So this kind of simple sentences can be converted from one language to another. using simple morpheme dictionary processing. So let us look at some examples of different kind of inflection in language, English language has. So S is a third person singular present. She waits. Ed is a past tense. He walked. Ing is progressive. She is watching. En is past participle. She has eaten. S again is a plural marker. So there is a disambiguation task here also. When you see the last word as S, last inflection marker as S, you need to figure out whether it is a third person singular or whether it is a plural. And how would you figure that out? You need to look at the word that you have seen before. If you have seen the third person, if you have seen a he, she, or it, then you would convert it into third person singular. But if it is a noun, if you know that you have not seen noun before, then and there are chances of the word to be noun, then you will say it is a plural marker. So part of speech disambiguation also helps in figuring out morph analysis. And we will see morph analysis and part of speech tagging as separate problems in this talk. But also notice that usually they go hand in hand, and there are many versions or many approaches where both are solved together. So S is a plural marker, 3 tables. Then possessive marker, whole is cat, apostrophe S. ER, comparative, you are taller. Superlative, EST, you are the tallest. There are some examples of inflections in English, and below that are examples of Gujarati, like Ram, Ramu, Ramesh, Ramadish, Ramarse. The word Ram can have many different kind of inflections. And then you can have complex sentences like Ramesh, Ramshe. So which is noun, which is verb, and which are the inflections? That can be a challenging task. So let us see what are the different approaches to build morph analyzers. Morph analyzers are, or rather most of the problems can be solved using rule-based approach, can also be solved using machine learning approach. So morph analysis also is no different, and you can break it down into rule-based methods and machine learning methods. We'll take an example of both. So there are two-level morphology, finite state morphology, paradigm-based methods, suffix stripping methods, where you strip the last inflectional character. In machine learning, traditionally you have supervised algorithms and unsupervised methods. And the algorithms that you use can range from CRS to recurrent neural network. All sorts of models people have tried. We'll see a couple of them. So this is an example of finite state based approach, which falls in our hierarchy, which falls in the rule based method. So for example, if we are processing nouns, and we know that S is the plural marker, then but we also know that there are some regular nouns which take plural marker S, but there are some irregular plural nouns also and irregular singular nouns also, which does not take S as the plural marker. So what we do is, we do a finite state model like this, Q0, Q1 and Q2. We are in 3 states. When you see a regular noun, you go from Q0 to Q1 and accept the word as a singular word. When you see a plural marker S, you accept the word and go to state Q2 and call it a plural word. But this rule won't work for irregular plurals or irregular singulars. So for that you need to directly jump. I guess the irregular singular should come to Q1. So for every accepting state of different morphology types, you have one acceptance state, and you define the rule like which alphabet you see as inflection and jump to a particular state. That is kind of finite state based approach. Another is a paradigm based approach where you group the words into the words which take similar inflection are grouped into a paradigm, and you identify that whenever you see this kind of word, it falls in this paradigm, and these are the usual morphological tags for the word. So paradigm, you need to construct a paradigm table which defines rules to form root words from the inflected word form along with the grammatical feature set for each word form type. For example, Ramu and Jamu both falls in same paradigm. Ramu, Ramshe, Ramarse, and similarly Jammu, Jamse, Jamarse, they are falling in same paradigm. So you know that there is a one paradigm of words like Ramu, Jammu, and so on. So look at the paradigm table and see what kind of inflections a word can have. Also look at the dictionary and find out uh, which root word corresponds to the word that we are looking at, the inflected word that we are looking at. And also look at the indeclinable words, the words which doesn't take any kind of marking, and also use it as knowledge for morphological analysis and construct a lexical entry or generative answers for the morphology analysis. This paradigm-based approach to build morphological analysis and like this. Nowadays, people are using deep learning-based approach, and I have given a very simple example of recurrent neural network-based morph analyzer. And from now on, whenever I mention the deep learning or recurrent neural network-based approach, imagine that the entire chain of the advanced networks like encoder, decoder, attention mechanism, pre-trained models like Bhatt, people have started experimenting on this, and there are much more sophisticated versions of this also are also uh, mentioned in literature. But I'm keeping the example simple to get the idea. That, for example, if word is ra, mi, sha, then we break it down into four letters: ra, ma, e, matra, and sha. And our task is to decide which part is in root word part and which is in part of inflection. So ram is the root verb. So whenever you are in root verb, the output produced by the recurrent network should be zero. And whenever you find out a suffix, you think that this iti matra can be in suffix, you mark it as 1. So your training data can be rama, isha, and output corresponding is 0011. And train this recurrent network on that. And after training the net, hope that the recurrent network would predict the new word correctly and give you the correct root and suffix for that. So it's a deep learning based way of morph analysis. Let's come to the next problem, which is known as part of speech tagging. So a part of speech tagger or POS tagger is a piece of software that reads text in some language and assigns part of speech to each word and other token, such as noun, verb, adjective, etc. So, for example, if the sentence is "I want an early upgrade," then for every word you need to figure out the part of speech. Like "I" is a pronoun, "want" is a verb, "N" is a determiner or article, "early" is an adjective, "upgrade" is a noun. So, identifying part of speech of every word is the problem called part of speech tagger. And of course, it is very basic task similar to morphological analysis because in all the applications of natural language processing like machine translations and all, you might need this as a pre-processing step. If you are going with some knowledge of, if you want to adapt to a system which has some more enriched knowledge of NLP, then you want to do this. So, what is the problem here? The problem is every word can appear in more than one part of speech. Example we discussed earlier was a dog. Like dog can be a noun also, dog can be a verb also, and within noun it can have more than one meaning also. I dog you for to do something. That is also use of dog as a verb. So let us see with this example. The above table was taken from internet. Like the first time he was shot in the hand as he chased the robbers outside. If this is the sentence, then corresponding correct part of speech marking is the is a determiner, first is a AJ means adjective, a time is a noun, he is a pronoun, was is verb, short is again verb, in and so on. So now if you see every word can take or many of these words takes more can take possibly more than one part of speech. Like first can be JJ or RB, time can be noun or verb. Right? I timed it well. When time is used as verb. Short can be a noun or a verb. And in verb also it can be either verb D or verb N. In can be in RB, RP. So there are many types related with in also. So problem of part of speech tagging is to predict the correct part of speech for the given word. So goal is to choose right part of speech for every word. And the important interesting observation here is POS of the word depends on POS of the previous word. The word which had seen previously, it is calculated based on that. For example, if you see that the first word here is the determiner, then first time you can judge the part of speech of first, whether it is JJ or RB. Similarly, if you see that the word was there, then was short, then short can be probably a verb, not noun. And if it is VBD, then short can be VBN. If you see VBD first, then the next word can possibly be VBN. So looking at the previous word and the part of speech assigned to the previous word helps you figure out part of speech for the next word. And this has led to a very famous natural language processing algorithm called part of speech tagger, a Rachel based part of speech tagger. And actually this was a famous work which has created interest in applying advanced machine learning algorithms to solve natural language processing problems. So this has been remembered for decades, and many people have tried to solve other problems also using this kind of strategies. So let us see what it is. Like the dog barks. Let's say the sentence is the dog barks, and part of speech is determiner, noun, and verb. So I have marked verb. I have marked the sentence into rectangles and verbs into circles. The part of speech assigned is in circles. And I said that the part of speech of the current word depends on the part of speech assigned to previous word. So that's why there is an arrow from DT to NN and NN to VB. And initially null word, null part of speech, so initial arrow. So now this becomes a sequence prediction or sequence labeling task. So you are not looking at a word independently and trying to figure out its part of speech, but you are looking at the previous sequence of words that you have observed and the part of speech that you have assigned. And based on that, you want to label the next word. So this is called sequence prediction or sequence labeling problem. And I mentioned it in this talk because many NLP problems can be modeled like this using sequence prediction or sequence labeling technique. And the famous model which was used earlier for this was hidden Markov model, where you say that the part of speech labels that you want to assign are the states of the system. So if you have observed determiner right now, then you are in state DT. Or the S1 is part of speech of the first word. You don't know what that part of speech is, but let's call it a state S1. And the state S2 depends on what POS you have assigned to S1. So value of S2 depends on value of S1. So S1, S2 up to Sn are the n different states for n words. And what actually that state is that we don't know. Right? So if the part of speech, see there are only three part of speech labels. Like in this example, DT, NN and VB, then there are only three states to choose from. But S1 can be DT, NN or VB, S2 can be DT, NN or VB, S3 can be DT, NN or VB. Which value it eventually takes or which state it eventually goes in, that is decided by the word, current word that you are looking at. If you know that barks can never be a determiner, then you can eliminate that possibility that barks is a determiner. So you have two choices for the state Sn, either NN or VB. So similarly, you look at the previous tag, and if you know that the previous tag was NN, then the next has to be VB, and so on. So we assign probability of part of speech given the verb. You have observed the verb given a part of speech, that is called emission probability. And you assign a probability of part of speech given the previously observed part of speech, that is called transition probability, transiting from one part of speech to another. So look at the data set, read so many sentences with part of speech labels and calculate this probability. How many times you have seen determiner following noun? How many times you have seen books or marks assigned a tag of verb, and so on. And once you do this, you create these two transition probability and emission probability tables. Probability of Si plus 1 given Si, the transition probability, and probability of Wi given Si as emission probability. The computations are simplified because of Markov assumption, which says that the current part of speech only depends on previous part of speech. You don't need to look beyond that. So the overall probability structure of word sentence given part of speech is modeled as probability of Si, comma W1 to Wi minus 1, S1 to Si minus 1 is pi of probability of Wi Si into probability of Si given Si minus 1 into probability of S0, which was your starting state. So with this formula, you can, and given the probability tables of transition and emission, you can predict the probability of new sentence. So what you need is a transition table like this. So we look at the corpus, we calculate how many times determiner followed determiner, how many times noun followed determiner, how many times verb followed determiner, and create this table called transition probability table. And similarly, we look at the word and see how many times the word was assigned a particular part of speech. Like the was assigned determiner tag twice, boys was assigned noun tag once, and so on, to create this emission probability table. Of course, this is a very small example, but we can, on large data set, the numbers will be bigger, and it is also normalized, so it becomes probability in the range of 0 to 1. Once you have this table, the next task is given a sentence, you want to assign a correct part of speech label. So, for example, if the sentence is Ram plays cricket, and you have 4 part of speech to choose from: determiner, noun, verb, and noun, and a proper noun. So how do you do this? You calculate this link weight, like probability of Ram given determiner, probability of Ram given noun, and probability of Ram given verb, and put it on the link. As if you can see, I have put some numbers like 1 by 2, 0 by 2, 0 by 2, and so on. Similarly, the state also has a probability. How many times Ram was assigned determiner in the corpus? Answer is 0. How many times the determiner was observed? Twice, so it is 0 by 2. So give this probability to link and also to the circles or the nodes, multiply them as given in our formula. It is multiplication of Wi given Si into Si given Si minus 1. Multiply them and choose with one with the highest weight. So if you see the bottommost circle is highest probability of 1 by 2. That is probability of Ram being a noun, a proper noun, which is true also. So enable that link, and from similarly do it for all levels. And at every level, the node which has the maximum probability value is the winner node, and that part of speech will be assigned to the word. So this is called decoding phase of HMM, very famous algorithm named Viterbi's algorithm. So those who want to look more into this can refer to Viterbi's algorithm, decoding algorithm, to see how it actually works. Right. So that was the second problem, morphology part of speech. Now let us come to the third problem of our interest. There is question answering. Nowadays, this is also a very popular problem, and as you can see from the images that I have put on the slide, you have a personal assistant or chatbot or conversation agent, whatever you name. They are everywhere, right? Every bank website, every insurance website, every messaging application. They try to help you completely. They try to give you answers automatically. So we have come a long way from Eliza. Eliza was very first such application. But we have come a long way, and nowadays the interest in this has grown. Also, you might have noticed this home devices like Alexa or Google Home. They are also kind of personal assistants which interacts with you and tries to answer your queries. So that has also opened up the market of this kind of research. What are the challenges in question answering system? Of course, the first one is finding best possible answer from a huge knowledge base is a key challenge. Remember the example of Bahubali, which I put on Google in the earlier slide? Like if you ask a question, it gets the perfect answer. So how do you know that the answer is better than the other answer? Or how would machine know that? So that is a challenge. And this challenge can be broken down into different levels. Like there are syntax level challenges, there are semantic level challenges, and there are discourse level challenges. For example, at syntax level, as we had seen during the description of that processing also, lexical ambiguity is a challenge. For example, will is a proper sentence, but if you want to assign part of speech or meaning to all this will, it is a very difficult task. Lexical gap between question structure and structure of knowledge base. So the way the question was asked and the way the mention was there in the knowledge base, these two are different. For example, in question you have word NLP. Then you need to know that NLP and natural language processing are two same things. So there has to be some knowledge base which can help you in mapping this. And if this mapping is not there, then even though you have answered, you would not be able to answer it correctly. So there is also a kind of syntax level challenge. And there are semantic level challenges like similarity identification. Is it a watchable movie or can we plan that movie? So in both the case questions, the intention or the information expected is same, but the sentence construction is completely different. The words used are also different. So machine needs to know that these two questions are similar. Then there are idiomatic uses which are difficult to break down by machine. By using this statement, he just throw the ball in your court. Now, machine needs to know that why I am bringing ball in court in the sentence. Machine needs to figure out the idiom and get the meaning out of that. Then neologism, we every day we coin new words like what is retweet. Retweet was not there earlier, but after Twitter now we have retweet. Similarly, we have now unfriend on social network. We never unfriended anyone before social network, but this after social network we have started unfriending people. So there are new words. Then new sense for a word is the Infosys an IT giant. Then yes, giant was not used in this positive connotation earlier, but now with companies, yes, we say it is giant. So for example, execute a program. So after the introduction of software and compilers, we started understanding execute as a task of running a program. Before that, execution was a punishment. Of course, running a program also, run a program. So it actually does not run, but we have started using it as a new sense of run. And yeah, I guess run is probably one of the words which has maximum number of senses. I exactly don't know, but you might check on internet like which word has maximum sense. The run would be higher in that list. Then some entity names are tricky when the let it be was recorded. So let it be is not all the three words are part of a common noun phrase. They don't need to be broken down. There also needs to be known. Then of course there are discourse level challenges, conversation history taking to whom. Like as I said, we need to look at the previous sentences, previous words to figure out the actual question of the user. And nowadays we have also adopted a non-standard English in our conversation, particularly in messaging and tweeting and all that. So when the hashtag rewards will be awarded, so hashtag and all these things are part of the language now. So machine also needs to process this. So imagine that we talked about part of speech tagger and we also talked about challenges in part of speech tagger. But now imagine a scenario where you want to do part of speech tag on this SMS language or the chat language where you are not typing a word correctly. Like if it is hello, then you will write O 10 times and L 5 times. So correcting those words and identifying right part of speech is also a challenging task. So what are the type of question answering systems and which techniques we follow? So there are many, but I would bring it to you. I will discuss few interesting techniques. Like one is factoid based where you try to answer who, what, where, when kind of questions or usually the facts. Then there are definition based where you extract definitions. or there are complex question answers where you need to process uh, language, and also sometimes you need to generate, because answer does not lie in one sentence or one phrase. You need to look at the entire paragraph and construct the answer. The kind of things that we do in reading comprehension. When we read a paragraph and when we are answering the question, sometimes the answer is directly there in the sentence, but sometimes you need to construct the sentence also. So this kind of example of complex question answer. And as far as the technique goes, uh, two prominent techniques are knowledge-based approach, where you use some existing knowledge base like Wikipedia, Yago, or other ontology or knowledge graph, or you use deep learning-based approach. We'll briefly see both of these examples, and then we'll move to the next part. So, for example, if the question is like, is Sachin playing outdoor sport? So, you need to know that Sachin plays cricket. So, let's say you have some sentence somewhere. You have read that sentence in your document that Sachin plays cricket. So, you have an answer, but you need to know that cricket is an outdoor sport. And for that, you need a knowledge base. You need some dictionary tree, as I have shown in this taxonomy, where you divide sport into two parts like types and players. Actually, it will be more than two, but I have just put the relevance bubbles. Then type has two subtypes, indoor and outdoor, and outdoor has the subtype cricket. So if you know that Sachin plays cricket, and if you are given a knowledge that cricket is an outdoor sport, then you can answer this question correctly. Otherwise, you won't be able to answer the question correctly. So that is why the knowledge base is an important part of question answering system. Another approach, as I said, is a encoder decoder kind of model, a deep learning, very famous deep learning model, as I said earlier also, which is used in many NLP, which is used to solve many NLP problems. So on the right side, sorry, on the left side you ask the question, on the right side you get the answer. So while you are training the machine, train it in a way that first the entire question is exposed to the machine. Machine will learn from the question and adjust the weight, and then it will start producing the answer. So we are calling it two phases, encoder phase and decoder phase. So during the encoding, you train for question, you understand which words of the question are important. You can also add the attention, like which word has more importance in context of answer, which words are less important in context of answer. You do all that in encoder part, and then at decoder part, you generate the answer. Okay. So this is how it is trained in encoder decoder. You have question answer pair, and this is kind of encoder decoder model that you can use to solve this problem. But as I said earlier also, and again I'm repeating that, so this is a standard way of going ahead, but there are many more variants proposed in literature beyond this. So also, when you are reading the paper, you might come across, at idea level it will be similar, but there might be some addition, some new challenges, some new structure uh, applied to solve the problem. And with that, let's move to the last segment, which is text summary generation. So it is a task of automatically summarize the text. Automatic summarization is the process of shortening a set of data computationally to create a subset that represents the most important or relevant information within the original document. There are two types of summaries: extractive summary, which extracts meaningful keywords or phrases and sentences, and second is abstractive summary, which gets the gist of the talk and generates summary. As most of you would realize, the key challenges in this task are: one is to identify correct word and phrases out of the entire document, which words are actually relevant and should go in summary. For that, you need to check relevance, whether the current sentence, current phrase, or current word has any relevance with the document, or it is an unnecessary sentence. Then you can simply remove it. So one is relevance. Second is coverage. The summary that you have generated covers all the aspects of the document, or it doesn't cover. And of course, brevity. How brief and precise you can be in your summary. That is also an important part. Let's see how we can solve this. Again, deep learning based encoder decoder kind of architecture can be applied to generate summary also. We are given input text, which is passed to the encoder neuron. Again, encoder neuron will get the gist from the text and will generate summary. And as I said, again, there are many variants of this. many improvement on this. Some references I have put here, some papers from Zhang et al., which applied pre-trained based energy. Energy means natural language generation core summary. They have used transform-based decoder to generate draft output, then mask and feed draft sequence to Bhatt. Then again in 2009, Yang et al. Has used modified Bhatt and combined extractive and extractive method to create summarization. So combination of two methods. Ray et al. Employed shared transformer and utilized self-attention mask to control what context the prediction condition on. And Fabry et al. Introduced multi-news dataset and used hierarchical MMR attention pointer generator to generate an abstractive summary from multi-documents. So these are some recent work on the text summarization technique. So with that, I will stop talking about we are towards the end of the talk. And at the last slide, I would like to point you to some of the works which we did in the area of machine learning and natural language processing. So we had done some interesting consortia projects called Anuvadaks and Indradhanush. Anuvadaks was an English to Indian language machine translation project sponsored by the Department of Information Technology, Ministry of IT. And it was a consortia project involving many reputed institutes like IIT Bombay and CDEC Pune and so on. Indradhanush was a project to build WordNet for 7 Indian languages, where we are representing Gujarati language. Again, it was a consortia project headed by IIT Bombay. Apart from that, we have also done other works like IndoNet, a link structure of 23 Indian languages. Then we also developed Gujarati Morph Analyzer, multilingual ontology extractors, Gujarati speech-to-text conversion. We have recently done this speech-to-text conversion, and it is also published recently in a conference called International Conference on Natural Language Processing in December 2020. And before I end, I should acknowledge Guj Coast who have granted us this Param Shavak last year. So for last 1 year, we are using Param Shavak for our experiments, and we are thankful to Guj Coast for that. So with that, I will end here. I will thank you all the participants and also KCG for inviting me for this talk and providing me this platform to discuss the work. I will end here and I will wait for the question answers.
Thank you so much, sir. Sir, it was actually a wonderful session and an interesting PPT. This is not just I am saying, but there are a number of comments which we have received on Facebook as well as in the streams. There was just one question which was asked by a participant, but after that he has also commented that you have gone into in-depth explanation of that particular concept. Still, I'm dictating the question. What are the future possibilities to translate local languages into standard? What are the challenges for the same? But again, that person has also commented that he has got the answer from the session.
Okay.
And moreover, there are such comments that it was a superb session, wonderful session covering all the topics in depth. And thank you so much, Brijesh sir, for that. It was very interesting PPT, sir. Even we, while at the time of moderating, it was not just a part of our duty that we are moderating, but we are into the so much of interest that we are learning some new things. So even I am thankful to you, sir.
I'm glad that you liked the session.
Yes,
and I
sir.
hope participants would also enjoy this.
Yes, yes, sir. I would like to say you one thing, that generally what happens that during the start of the session we do have more number of participants, but when the participants remain stagnant throughout the sessions, it depicts that the PPT and the session is interesting, sir.
Okay.
And yes, we were having same number of participants right from very first moment, from very first slide to the last slide, sir. Thank you so much for sparing your time and being with us, sir. I thank you on behalf of KCG.